All right. So pretty much we are going to look at the double sideband suppressed signal. So, generation of amplitude modulation. Let's describe two devices for the generation of amplitude modulated waves. The two that we're working with today is the square wave modulator, square law modulator, and the switching modulator. All right. With these two modulation, we require the use of a nonlinear element for their implementation. Okay. These two devices are well suited for low power modulation process. So let us look at the first one, the square law modulation. A square law modulator requires three features: a means of summing the carrier and the modulating waves, a nonlinear element, and a bandpass filter for extracting the desired modulation product. Think about that for a minute. What we say we require. Remember, what did we say a modulated signal consists of?
It consists of the carrier signal and the message.
Right. So we are saying a square law modulator requires three features: a means of summing those two, a nonlinear element, and a bandpass filter for the desired modulation product. Okay. So look at your picture. These are your two signal, your message signal, and your carrier signal. So this device will add these two together. Nonlinear device, meaning that we are going to transport the sum signal, the product of these two signals. We want to get it out here to the load. And then we're going to have a bandpass filter, meaning that when we get here and we have a message on your carrier and it get mixed up with all kind of noise and them stuff, this bandpass filter is going to get rid of those frequencies that we are not interested in and just deliver to the load the frequency we have an interest. So again, a square law modulator requires three features: the means of summing the carrier and the modulating waves, a nonlinear element, and a bandpass filter for extracting the desired modulation product. Semiconductor diodes and transistors are the most common nonlinear devices used for implementing square law modulation. I'm sure you guys are pretty up to speed on semiconductor and specifically the diodes and transistor. So look at the part that we all hate now. We all hate this. What about this that we hate? Come on, talk to me, no man. Let me feel so lonely.
Can you repeat what I said, please, sir?
What I said, now we can go to the part that we all hate. I'm talking about all of us hate this part. So I'm saying, what about this that we all hate?
Look confusing, sir.
Yes, sir, confusing, sir.
Confusing. But that's not it. It's only confusing because what? We don't like the math.
Because I'm at,
We don't like the math, not true.
yeah, for real, sir.
So that's what is confusing about it. Now, I ask you, or I made a statement of here that we are comfortable with the use of semiconductor diodes and transistors. Right? And no one said anything. But anyway, the transfer characteristic of the diode load transistor combination can be represented closely by the square law or by a square law. Right? Here is a voltage. Right? Go back to your picture. So your voltage is V2. It says E2 here. And your input voltage is E1 going through your nonlinear device. E1, E2, V1, V2. Right? For a transistor diode load, the scalar representation is given by this. The input voltage V1 consists of the carrier wave plus the modulating wave. That is, V1 is this, as stated before. So the only thing new, or the only thing you have to recall from your math is the square law formula, which is this. Because we already established the summation of the carrier wave and the information wave. So if we substitute that in the square law wave, right? We get this nice little mess. So we put in this for V1 here, and we do the expansion. Right? And that is what we get for this equation. So you square this, right? Put it in here. So all this like first term here, which will be AC square cos square that. You have it here. All right. Do me a favor and just get out a piece of paper and quickly substitute this into this equation and see if you get this. Do it in a man, no matter. Just sit down. I'll give you about 3 minutes to do it. Anyone was able to come up with it? Mr. Blackwood. Mr. Blackwood not here. I wonder why you guys do that. Just log on and leave. I don't know who is in the class. Mr. McFarlane. Okay. How many people do I have in the class right now?
Here, sir.
Not sure, sir, but I'm here.
Let me take a register of who is logged in and see who is here. Shavani Turner.
Yes, sir, I'm here.
Oh, yeah, Shavani. You have up your hand, Shavani.
Oh, sir, Kaya did ask who was here, so that's why he just put it up.
Okay. Abhishek Edwards,
Here, sir.
Adrian Blackwood. Not here. Beresford. Not here. Horace.
Sir, I raised my hand, sir. You didn't see it. Beresford, sir. I
Here,
raised my hand.
sir.
You hear that, sir?
Yeah, Beresford, you hear?
Yes, sir. Yes, sir.
So, Javiani.
Sir, Javian, sir. Javian Cardi.
Javian, sorry.
Yes, sir, can call me sisters. Anyone suit you, sir. You see me, sir?
No, I don't suit me. I need to get it right. Okay, Mr. Harvey.
Janelle, sir. Here, sir.
Oh, Janelle, sorry.
Harvey, yeah.
Gulab,
Present, sir.
Forbes,
Yes, sir.
Palmer,
Here, sir.
Lewis,
Yes, sir.
Monique, and Montague,
Here, sir.
Turner,
Sir,
okay. All right. So out of all the people that indicate they're here, anyone come up with this expression by combining this and that?
No, sir.
Okay.
I got it, and so just the fraction there to get now, sir. To divide by now.
This one?
Yes, sir.
Because, okay. Let's start from here. V1 square. So we're gonna square this. So we're gonna get AC square, cos square, 2 pi FCT, right? So this is V1 square equal AC square cos square base times A2, right? So that first expression, you get this. See that?
Sir, so V1's grade equal everything over the bottom right-hand corner, sir.
I might then combine some things here. You have this, right? So we're gonna square V1 square, right? So it's gonna be this square, right? A plus B square, which is A square plus what?
2AB.
2AB
Oh.
plus B squared, right? So this is your A square. This is your A square. No. Yeah, this is your A square. All right? This is your B square. No. That is your
Can I try and help there? Or so that's what I did.
of course.
Oh, sir, all right, so after square, I substitute the value for V1 into the equation for A1, V1 of t plus A2, V1 square of t. And I got, should I type it or let's say it out.
Let me give you a host privilege. And then where are you? Where is it? I don't see you. Where's that? Oh. So
Sir, well, I could try and take up. Oh, okay. Sir, I just started the recording. I just put the photo on to share it. Is it still necessary, sir?
I think everybody get it now, though, right?
Okay. So, how do I give you back host privilege? Sir?
You still have host privilege. Let's see.
Sir, I didn't. What you were just explaining didn't go on the recording. So could you show it again in case someone needed it?
What me erase it already? It's in the notes that was said.
Okay.
All right. So what you need to do is you need to go click on my name and
I just get through with it, sir.
oh Oh, you return it. Okay.
Yes, sir.
All right. So the spectral relationship in a square law modulator. So this is, in other words, this is what's happening pictorially. So this is your information signal, right? And then you're gonna put it on your carrier frequency. So this is it now. So this is your well, this is giving you the entire story. So this is your information signal. This is your carrier signal. All right. But this is a little bit more than what you would get here. That is after you go through that and go to the bandpass filter, you would get this. Because this is what you want.
Sir, can go back over that, please? I don't know if I missed something, but I'm confused.
Ah. So this is your information. Right? Yeah. Okay. No. So your M of T is your information, right? And you're going to combine it now with your carrier frequency. Right? To go through the nonlinear circuit, which is this, the carrier frequency, this your information, go through your nonlinear device, and then go through your bandpass filter. Right? So here we have the frequency of your information, the M of T, now converted to M of F. With me so far?
Yes, sir.
And this now, this is combined with your carrier frequency. All right? So the information, which is this, get combined with your carrier frequency. And you get this after it goes through the filter.
Okay, sir, understood.
Okay, the next one is the switching modulator. Again, this is their carrier frequency. And this is their information. In this case, a nonlinear device is a diode. So you know how this go. This will conduct when it's forward bias and cut out when it's reverse bias. So let's look at the equation now. Again, this is your V1. Okay. You help me here now. Based on your knowledge of diode, you have this sinusoidal carrier. Explain to me what goes on here.
Sir,
Mm.
look like alternating current, sir. So current just flow in one direction because the diode is there.
Well, if it was a alternating current, okay. Let's say it's an alternating voltage, not a current.
What, sir?
Let's say it's an alternating voltage and not an alternating current. The carrier voltage is the alternating voltage, right? This equation represents a voltage. This is your voltage. You with me?
Yes, sir.
Yes, sir.
All right. So from there now, start at time 0 and tell me what happened.
Sir, so at time 0, no voltage is there, sir. And then as you go along, sir, voltage increases linearly, sir.
So I put this, at some point I put this diode into forward bias, right?
Yes, sir.
Go ahead.
Yes, sir. So it goes into forward bias and then the voltage increases to V2, sir. And then after, sir, I think there would be no voltage underneath the graph, sir. So it would always be in forward bias.
No, man. So this voltage increase, put this into forward bias, and then it decrease. And when it pass 0 here for ideal diode, this is now in reverse bias. So you don't have any conduction, eh?
Yes, sir.
So then, V2. So V2 would follow V1 for the positive half cycle, and it will become 0 for the negative half cycle. You agree with me?
Repeat that, sir.
Let's go back to the circuit. So this now, remember, forget your information for a minute and look at your carrier voltage, right? This is an ideal. Consider this an ideal diode. So once this go positive, this will conduct, right?
Yes, sir.
So from this conduct, it's like a short circuit. So the voltage you measure here would be the same as this voltage. Because it's like you have a source and a resistor. So this positive voltage send a current, and the current cause a drop across here, which is equal to this voltage. Agree?
Yes, sir.
So when it becomes negative now, it causes this resistor, this diode, to be reverse biased. So it's like it's an open circuit. So no current is flowing through here. So you don't have a voltage drop here. So yes, I know, man.
Yes, sir.
Yes, sir.
So then, I'm saying that's what is represented here. V2, which is the output voltage, is the same as V1 when you're on the positive half cycle, and is equal to 0 on the negative half cycle. Okay. So what we're gonna do now is we are going to use we have a carrier signal, and now we are going to pull in the information, our message signal. So this is your carrier signal still, which is this. This is your message signal. Right. Now, your GT now comes in because you go from the time domain using Fourier transform to the frequency domain. So This is it. What I'm going to have to do here is this. Because oh boy. Okay. You know what I'm saying? Okay, how am I back gonna know? Nah, bro. Get no book and read it. Man, let's send it.
Yes, sir. Send it same way, sir. I read it, man.
Yeah, me not send it to them now. Go look for it now and read it. Somehow I might read it and mess it. Copy it right here. So this, copy. After the wait, no. We'll have the classes for log back into the email and say. But suffice it to say, this is making use of Fourier transform to get you to that point.
So you can just send the link in the Zoom chat, sir. I'll send it in the group.
I'm gonna do that from a computer.
Sir, go on Zoom. Go on the next one and say controls. Go on beside that. To the right, yeah.
In controls.
Yeah, you see down at the bottom, it's supposed to say chat.
Hold on. Maintenance controls.
So you can get the youth an extra 5%, you know, sir, if you teach you how to operate the Zoom, you know what I mean, sir? Just to interject that, sir.
Yeah, can give me a little extra 5% for me pay if you try to teach, you know, you know.
Yeah, man, sir, what I would pay with school, sir, what I would pay with school fee, you know, sir, so 5%, not, sir, we don't go in the bargain, sir.
Yeah. Okay, so weirdo. I click on meeting controls. But you not come.
No, come up. Carry your mouse go all the way down, sir, and to see if the options them come up. No, come up. Boy. All right, sir, just have to email it then. Unless somebody else know what going.
Chat. Some of that chat now.
Zoom
Yes,
chat,
sir. Just paste. Just right click on or left click and paste it, sir. That's all.
Start chatting by clicking a chat in the left panel. So, chat. New chat. Message. Yes, now. it in this or now? It's not work out, guys, but me email it, yeah?
Yes, sir.
Alright, sir.
Man. Okay. Yeah, me get to a part where it said name or email address. So me just I go say now, what the name of the group? Communication group.
Communications theory. Sir.
Yeah, so I'm gonna go here, some say communications. COMMUN.
Sir, on the screen, do you see a little box with at the top right side of the computer screen? Sir? When you move the mouse. Because sometimes when you minimize zoom, you have to restore it back. So,
Someone else said upstairs, yeah. All right, let's not waste that. Anyway, so this is when you combine the carrier signal and the message signal and the Fourier series, which is that. So this is your desired wave now. So you see, you start with your triangular wave, and you combine that with your carrier wave, and this is what you got after you go through the bandpass filter. Okay. So you start out with a certain wave and you modulate it and get a certain pulse train. Now, remember you want to get it back in a form similar to what you sent out. So you have to go through the demodulation process. So we say here, we can remove the unwanted terms by passing this output voltage of T through the bandpass filter, and finally we will get required AM signal. Right? When such a device is used for the demodulation of an AM wave, we have for the input here, and we decide we define K2 already from above. If you substitute in this into this as before, we end up with this. So this is your demodulator. I know it's not in a easier box like not easy. So what we have here, this is your AM wave input. Right. And it's going through here. If you notice, the lower half here will put your diode in reverse bias. So only your upper half goes through. So these are some of the limitations in amplitude modulation, or AM. The carrier wave CT is completely independent of the information carrying signal or baseband signal MT, which means that the transmission of the carrier wave represents a waste of power. At least tell me you get that.
Say that again, sir.
Yeah, see screen, read it, read the first bulletin.
So, sir, is it saying that it's not needed or?
No, it's needed. All right, it's like, Yeah, analogy, no, meaningful analogy. It's like okay, it's like putting your car up on a wrecker, right? And the engine is still running and it's on the wrecker. Right? So you use up energy to keep it running. And you have the wrecker to carry it, go to point B. Right? So if the car could just go to point B without the wrecker, I don't know if that is a good example. You're using power to transmit the carry. All right. So what you really want to do is to get your information from point A to point B. Right? But in order to do that, you have to put it on a carrier, put it on a horseback. So the information in moving from point A to B is consuming power. And the carrier is also consuming power. So we are saying that since the power that the carrier is consuming is totally independent of the power that the actual information signal is consuming. It's a waste. Because if there was a way where you could get the information there without the carrier power, you would have reduced the power consumption. You get that? If I know, I know. If I know, I know, I know.
So, sir, is it that you're saying the carrier signal has its own power that it's losing as it goes along? Or is it using the power from the information signal?
No, I'm saying that you have to, let's call it energy. You have to exert some energy to move your information, right? And since you put the information on a carrier, both the carrier and the signal is going to the same place. So you have to exert two different quantum of energy to get the information and the carrier from point A to point B.
Okay, sir.
So if you never have to use a carrier, right? You would only consume the energy for the information. Make sense?
Yes, sir.
Is that if then therefore thing. Alright? If you use 10 joules to move 1 kilogram, how much joules you need to move 2? That are 2 times 10, right?
Yes, sir.
So if we think of it in terms of weight, so the carrier weighs X amount and the information weighs X amount. And we need more energy to move the two of them from A to B. So the second bulletin, only which is basically coming straight out the first. Only a fraction of the total transmitted power is affected by MT. MT being information. So out of all the power where you use up, only a fraction of it is affected by your information. The rest is what? Well, the rest is affect the carrier. Right? And this now, to overcome this, the carrier component from the modulated wave resulting in double sideband suppressed carrier modulation.
Oh.
Okay. You know what I'm saying? I don't know if I talk fast. I'm not explaining enough because I'm not interact.
Oh, sir, the last part of what you just read, sir, I think I miss out something.
This part, you know, the double side, that's why I didn't delay on it. So to overcome the problem we have here, we're gonna have to use the double sideband suppressed carrier modulation, which is what we're gonna do next.
Okay.
Double sideband suppressed carrier modulation. But I was just saying that I think maybe I'm I'm running it too fast because I never want to start this today. So I'll give an extra 20 minutes to go over the Fourier and review these notes. So let me go now to send out the thing on me does.
Sir, in the meantime, sir, while you're doing that, sir, what is to be after labs tomorrow, sir?
Well, like when better tell me the truth.
Yes, sir. Yes, sir.
All right. I'm gonna start it out yet.
Okay, sir, because with the lab, sir, we're better able to grasp the concepts, sir, and apply what we learn in theory in a real world scenario, sir.
Yeah, I agree with you. And they will all be MATLAB, so you will when you put in the equation, you will see. So you are absolutely right. And make sure you get them this week though.
Okay,
And of course, although we have a scheduled time, you can do them at your own leisure. Just get them done. Like I say, if you follow the lecture with the labs, you know, it will be better for you.
Okay, sir. Which means these labs will be virtual instead of a face-to-face lab, right?
Yep.
Okay, sir. Thank you.
All right, so I'll go into the sent mail. Okay, so all right. So Ms. Montague will have to post it for me, okay?
All right, sir, will do.
So there you go, you have it. It's a Google Drive, so you have that. So I'm gonna stop there.
Sir,
Is that right?
sir, I'm checking to see if you had decided a date for the mid semester.
Oh. Which week we in? What, the 5th?
Yes, sir. Right about there.
Maybe another 2-3 weeks. Plus, remember that we start 1 week late, so we have a little catching up to do as well. So maybe one of these days we have to schedule one of the lab sessions to do an extra class or run a tutorial or something like that. Which I would probably like to do. I would like to do before I give you a test. All right.
Okay, sir.
All right, so next week.